Dr. Kelly Miller begins our presentations today by describing a groundbreaking new mass spectrometer set to launch next year aboard NASA's Europa Clipper spacecraft. The spectrometer is one of 9 instruments that make up the science payload aimed at revealing the secrets of Europa, an icy moon of Jupiter believed to harbor a subsurface ocean. Kelly.
Great, thank you. So when I tell people in my daily life that I'm a planetary scientist, I usually get one of 3 responses. Surprisingly, several people will ask me what my favorite plant is, and I'm partial to cactuses, so that works pretty well living here in San Antonio. The second group of people will ask me what my favorite planet is, and I always respond that just as a parent loves all of their children, a planetary scientist loves all planets. And the third group of people asks if Pluto is a planet, and that's a great conversation starter to talk about all kinds of exciting places in the solar system that aren't technically planets, but are still really interesting to explore. So one of the places that I'm most excited about right now is a moon named Europa, and while it's not a planet, I still love it. Europa is one of the 4 Galilean satellites, the largest moons of Jupiter, and it was discovered in 1610 by Simon Marius and Galileo Galilei. And you can see here a page from Galileo's notebook where he tracked the movements of the moons around Jupiter from night to night and determined that they were in orbit around Jupiter. You can see them in order here: Io, Europa, Ganymede, and Callisto. And if you have a pair of binoculars at home, when you get back home tonight or later this week, if you go look at about 8 p.m. or so in the west, you should be able to see through your binoculars Jupiter and also the 4 satellites. And you can think about Marius and Galileo and how they tracked these movements of these points of light 400 years ago. About 27 years ago, NASA sent the Galileo mission to explore the Jovian system, and it made a big discovery, which is that the magnetic field of Jupiter is disturbed by Europa. And we now understand that this is caused by a salty subsurface ocean that's underneath Europa's crust. Scientists also discovered that Europa has a really young surface. So if you look at the surface here from this image that the Juno mission took last year, you'll see that there are relatively few craters on Europa's surface. And if you look at an old surface, like Earth's moon, for example, the craters really stand out. And those craters are caused by impactors that hit over time and accumulate these craters. So when we see a crater-free surface like this, that tells us that there's an active geologic process that's erasing those craters and creating a blank slate. There are also a lot of interesting features on Europa's surface, like lineae and chaos terrain. And by studying these features, scientists have discovered that parts of the crust appear to be going underground and taking chemical compounds from the surface with them. So there are a lot of really interesting features about Europa, and in fact, it sparked a new subfield of planetary science, studying ocean worlds. And one of the reasons that planetary scientists are so excited about these ocean worlds is because they're a really tantalizing opportunity to answer that millennia-old question, are we alone? So this question dates back at least to the ancient Greeks, and it has profound implications for origins of life on Earth and our understanding of our place in the universe. And either answer, yes or no, is going to have a huge impact not only on science, but also culture and philosophy. In our current search to find the answer to this question, one of the areas that we're focusing on is habitability and understanding what environments in our solar system could be habitable. And by habitable, I mean could support life. From evolutionary biology, we know that all life is related. And so we really only have one example of what life is and what it requires. But from that example, what we understand is that there are 4 key ingredients. And the first is chemical building blocks like carbon, hydrogen, nitrogen, and oxygen. And the second is a liquid medium like water that can move those building blocks around. The third is energy to arrange those building blocks and combine them. And all 3 of these need to persist together at the same time for a long enough time to support growth. Ocean worlds are one of the best places in our solar system to find all these ingredients together. The video here shows a clip from Earth's ocean floor of a hydrothermal vent. And you can see plumes of hot water carrying dissolved carbon and other elements ejecting into the cold ocean water. And the contrast in temperature and chemical composition creates an imbalance that can be exploited by life forms to get energy. And so you see this thriving ecosystem. And we think that it's possible there could be geologic settings like this at Europa's ocean floor. Could Europa support life? To find out, NASA is sending the Europa Clipper mission, and it'll launch in October 2024 and begin the first of about 50 close flybys of Europa's surface in 2031. So it's a pretty long journey, but a relatively short amount of time to try and find answers to this 2,500-year-old question. There are going to be 9 instruments on the scientific payload, and of those 9, 2 of them were built here at SWRI. One of them is the ultraviolet spectrometer, which you can see here, and it's part of a family of instruments that has already explored out past Pluto even to help us understand our solar system. The other instrument, MASPEX, will be making its very first journey. MASPEX is a homegrown success story. It was started in 2003 with internal research funding by staff scientist Greg Miller. And then it was matured over 5 generations before being proposed for the Europa Clipper mission by Hunter Waite and Tim Brockwell. And that proposal was selected in 2015. Since then, the flight design was finalized, and the flight and engineering model instruments were built. You can see Greg here with the first spectrum that was taken on the flight model instrument. My role in the project is in instrument calibration, and in 2021 and 2022, we conducted 3 month-long campaigns to collect the calibration data set. So MASPEX is a type of mass spectrometer, and you can think of it kind of like a nose. So if you have dogs like I do, then you know that they love to go for a ride, and the best part of it is to stick their heads out the window and take a big sniff as the world goes by. And they can learn a lot about their environment doing that. And that's essentially what we're going to do with MASPEX. We're going to sniff Europa as we fly by and learn as much as we can about that environment. And just like a dog can tell between beef and broccoli with its nose, mass spectrometers can tell between different types of chemical compounds. And we do that by weighing them very accurately. And from that weight, we can determine what their chemical formula is. To weigh them, there are 4 different steps. So first, the instrument sniffs in that ambient neutral gas in the environment, and then it removes an electron from those analyte molecules and turns them into ions. And once you remove that electron, it has a charge on it, and so you can control it with electric and magnetic fields. And we use that property to accelerate it down a flight path using an electric field. And the lighter ions are going to go faster, and the heavier ions are going to go slower. And so we can separate them out by their mass through that acceleration down the flight tube. And at the end of the flight tube, they hit the detector, and the impact creates a signal that we can record. And so if we record the signal over time, then we get a mass spectrum with those lighter ions coming faster and the heavier ions coming slower. Spaceflight mass spectrometry has been in use since the Apollo program in the 1960s and the 1970s. But one of the ways that MASPEX really stands out from the crowd is in terms of mass resolution, or its ability to distinguish between 2 very similar masses. So you can think of those ions kind of like runners in a race. And if you wanted to tell which of the 2 runners were faster, if their speed was very similar, you'd do better to have them run a marathon instead of a 50-yard dash, because the amount of time between when they cross the finish line is going to be a lot longer with the marathon. It'll be easier to tell who crosses first. And so that's what MASPEX does. We can have our ions run a 50-yard dash or have them run a marathon. And when we want to use our high mass resolution capabilities, we run the marathon. And we do that with 2 reflectrons that are at either end of that flight path. And so we can put the reflectrons on, and the ions will bounce back and forth so that it's a longer flight path that they travel, and then send them to the detector to detect them. Here you can see a video where we demonstrated this in one of the calibration campaigns. And you can see as the one peak separates into 2 peaks as the length of that flight path increases. So most spaceflight mass spectrometers can only tell the difference between 1 atomic mass unit. And the peaks here in this final spectrum are separated by only 0.004 atomic mass units. So this is quite an improvement upon past spaceflight mass spectrometers. And that 0.004 AMU, that's equivalent to about 10 electrons or so. So we're talking very tiny masses that we can distinguish between here. And in order to achieve this, these ions flew 560 laps, which is about half of a mile that they traveled back and forth in that flight tube. and they were going about 40 miles per second the whole time. So it's a pretty impressive instrument. As the Clipper spacecraft flies past Europa, MASPEX will sniff in the ambient shell of gas that surrounds it. And this thin shell of gas, which is called the exosphere, is mostly created by the impact of charged particles that Jupiter's magnetic field accelerates into the surface. And when these charged particles impact the surface, they sputter these molecules from the surface into that exosphere so that MASPEX can sniff them as it flies by. And the surface may be covered with compounds that come from that subsurface ocean and have traveled through that active icy crust. So we'll be looking for things like food that alien microbes could eat. We don't really expect with this mission to find alien microbes themselves, but we'll certainly be keeping an eye out and setting the stage for a future mission to directly look for those. We'll also be looking for conditions like how acidic the ocean could be or what temperature it is so that we can better understand that habitability. So MASPEX recently reached a huge milestone, and after years of hard work and troubleshooting, it's been delivered to the Jet Propulsion Laboratory out in Pasadena, California. And it got loaded up into a truck and then arrived there on December 16th of 2022. And here you can see PI Jim Birch and some of the other team members from MASPEX with the flight instrument at the receiving lab there in California. And so now that it's been delivered, the next step is for it to get integrated onto the spacecraft with the rest of the scientific instruments. And this is a process that you can actually follow along with over the course of this year at home if you would like, using that URL at the bottom of the screen, or you can just Google Europa Clipper live view or live stream, and you can find a link very easily. This is a clip from that live stream from just a couple of weeks ago. So here they're working on preparing that spacecraft, integrating the instruments onto the payload, and then they'll test the whole system before they ship it out to Florida. And then in October 2024, it'll launch for the next phase of its journey on a Falcon Heavy rocket. In the meantime, the MASPEX team will be busy working with the engineering model here at SWRI to prepare for our arrival at Europa. Our team will also be busy thinking about the future of spaceflight mass spectrometry. So there's still all kinds of places for us to explore in the solar system, and future possible NASA medium-sized missions could include flying through the plume of Enceladus to search for habitability, or exploring a Centaur, which is a time capsule from the birth of our solar system, or flying through the carbon haze in Titan's atmosphere to understand how that complex body evolves. Planetary scientists also want to go back to Uranus. We've had one mission to Uranus, and it was 10 months before I was born, so it's time to go back. And so we can answer all kinds of important questions about ice giants with a mission like that. All of these missions are going to inspire the next generation of scientists and engineers. And so whatever the next adventure is, MASPEX will be ready to sniff for alien life and the origins and evolution of our solar system. Thank you.
All right, we have a couple of minutes for questions. Any quick questions for Dr. Miller? Yes, Jeff.
So you were saying that ions from Jupiter impact the surface and sputter molecules. Do they also break up the molecules, making it hard to tell what you started with?
Yeah, so the question is, during that sputtering where charged particles impact the surface of Europa, are there processes that change those chemical compounds? And that's a good question. Yes, we do expect that will cause some changes to the chemistry, yeah, so processes like that will change those ocean compounds, and so we'll need to support our measurements with laboratory studies, for example, of sputtering of ices, to see how those changes affect the compounds.
One more. Dr. Rankin? Or, go ahead.
How thick is the crust?
Tens of kilometers. We don't know for sure what the thickness is. Actually, that's one of the big questions, and we're sending a radar there to try and constrain the thickness because it affects how much of that ocean material we're expecting to see, but probably on the order of tens of kilometers.
Yes.
So if you say there's an ocean, that means there's hydrogen and oxygen, right?
Yeah,
And
that's,
so, yeah, I mean, unless water's made by something else on Europa.
yeah, so the water probably was part of the original materials that formed Europa. We do see hydrogen and oxygen in that exosphere when we look at it with telescopes, for example, and some of that's from that sputtering processing that generates the hydrogen and the oxygen from the water.
Very good. Thank you, Dr. Miller, Kelly Miller. And Kelly will be available at lunch.